Right, this is a lecture on gamma and beta functions and how to rearrange integrals into those forms, and it's on the special functions course. Right, first, these are the definitions. This is our gamma function, which is integral between 0 and infinity of e to the minus t, t to the power of z minus 1, and z is a complex number. Some stuff we can do with it. We can say gamma of z plus 1 is equal to z times gamma of z. I'm sure you can find all these proofs on the internet. Gamma of z times gamma of 1 minus z. This is quite a big proof. This is equal to pi over sine pi z. I've not found much use for that yet, but now if we're going to have just the natural numbers, so 1, 2, 3, 4, 5, so on, then we can have gamma of 1 is equal to the value 1, and gamma of n plus 1 is equal to n factorial. And you can see this from this really, because we're multiplying the outside by the 1 less than this, and then this gets reduced, and then we'll reduce it again and multiply by 1 less. So you're going z times z minus 1 times z minus 2, carries on until we get to 1, which gives us value 1, or you might get to a half, in which case the specific value is the square root of pi. This is quite useful. The beta function, this is the integral between 0 and 1 of t to the power p minus 1 and 1 minus t to the power q minus 1 dt. And this is related to the gamma function, as it's gamma p times gamma q over gamma p plus q. So now we're going to look at some examples of how to use these. So we want to express the following integral in terms of factorials. So we've got e to the minus t, t to the n plus 1. And the factorial, if we remember from just here, factorial, this is to do with the gamma function. So we want to get it in a form like this. We've got e to the minus t and t to the z minus 1. So here we've got n plus 1. We want to have something minus 1. So if we let this n equal z minus 2, then this will give us z minus 1 here, which is what we want, or m. I've used m in this case. So m minus 2, then we get the m minus 1 here, which means we can call it gamma m. I hope you can see that properly. And we'll turn it back into what m is, just rearrange this so we get m plus 2, and then from our definition before we can see that gamma n plus 2 is n plus 1 factorial. Right, our final example is the beta function. So we want to express this in terms of the beta function. So first thing you'll probably, well, I'll get the beta function up. The first thing you'll be thinking is this doesn't look anything like this. So we're going to have to do some sort of substitution to let, I think I used t, equal either sine or cosine. And if we try t equals cosine squared, well, first off, I've rearranged this. All I've done is I've just moved this up to here by just finding the negative here, so it gets p minus 1. So if we let t equal cosine squared, then, well, one trigonometric identity we know is that cosine squared plus sine squared is 1. And we just rearrange this so we can get cosine and sine in terms of t. So obviously from here, square root of t and 1 minus t. And we know beta function is always positive. So that's why we're just taking the positive square roots. Sub these back in, and you'll get 1 minus t, because we've got this here, and instead of doing the square root thing, I've just done it to the power half, and then because we're putting up here, because we've got a half, it'll be multiplied by q minus 1, so that's we've got q minus 1 over 2, and for the t, we've got p minus 1 to the half. And if we just look at these, we can see that over here what you're doing is you're adding 1 to each of these powers to give you a beta function. So if we add 1 to here, we'll get q over 2, q plus 1 over 2, because this is basically q over 2 minus a half, and we're adding 1, so it'll be q over 2 plus a half, so that's what we've got this, and it's the exact same over here. I hope that all made sense.